So 7.4, we're going to learn how to evaluate and graph logarithms. It's important to know that exponentials and logarithms are inverses of each other. And so when we did the inverse section, where we switched x and y to solve for y again to find the inverse function, it's the same kind of thing, but now the inverse of a logarithmic function is an exponential and vice versa. So it's useful to know how to solve for these equations. Here we have the logarithmic form. I would say that the way that I would pronounce this is that the log of base b of y equals x. So this b right here, we call that our base. And it equals x. It can be rewritten as b to the x equals y. So a good way to kind of learn or memorize how it switches is I think about the b coming up. So I have log of base b of y equals x. What happens to the b is it shifts up. The y comes around and the x comes to the top. So think about it kind of making like a circular motion. The b comes up, the x rises to the top, and the y comes to the other side. So that's the relationship that they share. And it just takes a lot of practice, but having this memorized the way that it switches is important. So I would put memorize. These you will have your calculator. It's almost impossible to solve these without a calculator. But there are a few that you can do without a calculator that we'll show in later sections. But for right now, all that you need to know is the way that it changes from logarithmic form to exponential form and the differences between the two, and then what they share. So you should be able to switch from logarithmic to exponential, exponential back to logarithmic. You can type it directly into your calculator, or you can put it in. You can either solve by hand. So if we look at number 1, here we have log base 2 of x equals 3. So I would rewrite this in exponential form by saying I bring the 2 up to the top, the x moves to the other side, and the 3 comes to the exponent. So this would be 2 to the third equals x. So x equals 8. That one I could just do by hand. So anything for a non-calculator portion would be something simple like this. Log base b of 9 equals 2. B comes to the top. 9 switches to the other side, and 2 becomes the exponent. So this would be written as b squared equals 9. And so then the square root would be plus or minus 3. So b equals a positive 3 and b equals a negative 3. But negative 3 would not be a solution because you can never have negative logarithms. So in this section or this unit, no negatives, no negative logarithms. So anytime you get a negative solution, it does not count. It's extraneous or whatever you would like to call it. Then number 3, we have 1/2 log base 1/2 of x equals 4, negative 4. So the negative, or the 1/2 comes to the top. The negative 4 is an exponent, and then the x goes to the other side. So anything to a negative exponent would be where you flip. Remember that you flip the fraction. So it would be like saying 2 to the 4th power equals x. And 2 to the 4th power is 16. So the answer is 16. Rewrite the following in logarithmic form and then solve. So here we're doing the opposite. So we have 3 to the x equals 27. If I'm going backwards, this 3 becomes my base. The x goes to the other side, and then the 27 comes over. So it would be like saying log base 3 of 27 equals x. So you can type this directly into your calculator if you have an Inspire. It would call for the base, and it would also call for the 27 as well. So if you have an Inspire, it's going to have a place where you just type in the base. If you don't have an Inspire, it's going to automatically assume that the base right here is 10. And so if you have an 84, if you have a TI 84, the way that you can write this, if you have log of 3 of 27, it's the same thing as saying log of 27 over log of 3. And so the reason why, and sometimes in 84, if it's not updated, it's going to automatically assume that these bases are 10, and we'll get to that in a minute. But if it doesn't have a place to type in the 3, if there's no prompting you to type in the 3, if it's just blank, then you could say that this equals log of 27 over log of 3. And that would also get you the same answer. So you should get x equals 3 as your answer. Number 5, if I were to rewrite this in logarithmic form, the 4 goes to the base. So the 4 becomes my base. So it will be log base 4. 64 comes to the left. This moves to the right, equals 5x. And so then if I were to solve, log of 34, or log base 4 of 64 is equal, if you type that in your calculator, you end up getting 3 equals 5x. Divide by 5, divide by 5, x equals 3/5. So that would be my answer. Here I have 1/5 to the x plus 3 equals 125. This 1/5 goes to the bottom, so it's log of 1/5. The 125 is out to the left, so you move that to the left. Then x plus 3 comes to the right. When I type in log of 1/5 of 125, I end up getting -3 equals x plus 3. Subtract 3 on each side. X equals -6. Okay, next example, we have 4 to the x equals 11. So this 4 would become the base. So it comes down to the bottom. X moves to the other side. 11 comes over to the left. So I would write this as log base 4 of 11 equals x. Type that in my calculator. You end up getting 1.7297. And it is okay to leave it as a decimal. Yay, decimals. 2 to the x equals 5. The 2 comes down to the bottom. X moves to the right. 5 moves to the left. So log base 2 of 5 equals x. And you put that in your calculator. You get x equals 2.3219. When I am saying to put this in your calculator, I mean I want you to pause the video and please put it in your calculator because you're not going to know how to do this on a test. If you have an 84, it would look like log of 5 over log of 2. So that's only if you have an 84 and it doesn't have a place for you to type in the base. So I just wanted to remind you of that. Number 9, I would rewrite that. The 7 goes to the base, so log base 7. 15 comes over to the left. 9x moves to the right. So log base 7 of 15, divide it by 9. You get x equals 0.1546. Number 10 is a little different because we have an e. So first step that I'm going to do for number 10 is I'm going to add the 7 on each side. So I get 4e to the negative 0.3 x equals 20. And then I'm going to divide by 4. Divide by 4. So you get e to the negative 0.3 x equals 5. So then if I were to rewrite this, e, remember, is a constant. It is like 2.7818, something like that. And so I treat this just like any number, where now my base would be e. So I move this to the bottom. The 0.3x comes over to the right, and the 5 comes over to the left. So it looks like log base e of 5 equals negative 0.3x. Now we're going to get to this in a minute, but this is just kind of an intro. Anytime you have a log base e, I call this a natural log, which looks like ln. So on your calculator, if you can locate the ln button, we call this a natural log. So that's a natural base. It's like a log base e, but I pronounce this as a natural log. So in my calculator, I could type log base e of 5, or I could type ln of 5 equals negative 0.3x. So I want you to type in natural log, because anytime you have a log of base e, we call that natural log, and we'll see those quite often. And so then I type in natural log of 5, divide that by negative 0.3. So I'm going to come over here. Ln of 5 divided by negative 0.3 equals x, because I just divided each side by negative 0.3. And I end up getting x equals negative 5.364, negative 5.36479. For number 11, I want you to change this to minus 10, because if you have a plus 10, it's going to end up getting a negative, and we can't have negatives. Okay, so first step, think about whenever you're solving for these, especially with these two, it's like doing PEMDAS backwards. So PEMDAS backwards. You want to get it into exponential form. So PEMDAS backwards to get to exponential form. So PEMDAS backwards to get to exponential form. So if I have the minus 10, then I'm going to add or subtract first. So I'm going to add the 10 on each side. And so I end up getting 5 times 2 to the x minus 4 equals 17. Now I'm going to divide by 5. So divide each side by 5. And I get 2 to the x minus 4 equals 17 over 5. I'm going to leave it like this as a fraction. This would be considered exponential form. So now I'm going to put it in logarithmic. So this 2 becomes my base. Log base 2, 17 over 5 equals, move the x minus 4 over. So then I'm going to type that in. I'm going to add 4 to each side. So you end up getting, so log base 2 of 17 over 5 plus 4 gives me 5.7655. Please, please, please type this in your calculator and check that you get the same answers as me, because knowing how to solve isn't the hardest part. It's getting it in your calculator. So pause the video, check and make sure that you got the same answer as me on your calculator, because I want you to be able to do it on the calculator as well. Okay, special logarithms. This is kind of what I was talking about earlier. A common logarithm is with a base of 10. So if you have the TI-84, it automatically puts in a base 10 for you, assuming that it's base 10. And so if you just see log of x, then you assume that it is. So log of x is the same thing as saying log base 10 of x. So it's understood to be a 10 if nothing is there, if it's blank. Just kind of like having, 1x, x equals 1x. It's assumed that there is a 1 here. Like we just assume that that is a 1. It's the same as if we have log of x. We assume that there is a base 10 here. So I know you didn't assume in geometry, but we assume here. So it's like having just x. It's like a 1 in front. Here we have a base 10. A natural log, so that we talked about earlier, a natural logarithm is a log with a base of e. So log base e of x is the same thing as saying ln of x, natural log. So anything with a base of e, it's called a natural log. It's more commonly used as ln of x. So these two things you want to know. And a common base is 10. Anything with a base of e is the natural log. So we're going to simplify by rewriting the logarithmic form in exponential. So here we have 10 to the log of 3x. If I were to switch that, it is 10 log base 10 of 3x. So if you have, this is just another rule, if your exponent and your log base equal each other, then they will cancel out. So here is a 10 and here is a 10. If they have the same base as it does the number that's like your b value, if they are the same, then they will cancel and you end up getting just 3x. So I'm going to write the rule for that. I'm just going to put it right here. Actually, I'm going to erase this so that we have more room. If we have, so the number that is in front, which we call b, raised to log b of x, it ends up just equaling x. So if the number in front and the base, if they are the same, then they just cancel. And you're just left with x as your answer. It's the same as if I were to write it as, so it also applies if it looks something like this. Log base b of b to the x, that also just equals x. So, and we're going to get a lot of practice with this because this is all completely new. But if you have a base b raised to the b, those would cancel and you end up just getting x as your answer. So I'm going to look at number 13. You see that we have a base of 5. If I were to simplify by rewriting it in logarithmic or exponential form, if I were to simplify this, so I have a base of 5, but I want to turn this 25 into a 5. So I'm going to rewrite this as 5 squared because 25 equals 5 squared. So I'm going to rewrite this as log base 5 of 5 squared to the x. So all I did is I replaced this 25 to be 5 squared. That is all that I did. And now I'm going to distribute that 2 to the x. So log base 5 of 5 to the 2x. Okay, here is where I have a 5 here and a 5 here. So it kind of looks like this example that we did up here. Since the base and the number are the same, they cancel. And so my final answer just becomes 2x. Also, if you type these into mathway.com, they will simplify for you as well. Here we have natural log of e to the x minus 2. Remember that you can rewrite ln as log base e. So I'm just rewriting it as this, to the e, to the x minus 2. Here we have e here, e here. So what happens? They cancel. And my final answer just becomes x minus 2. So you're kind of seeing a pattern that they end up just being the exponent as the answer. Here we have e to the natural log of x minus 4 squared. Anytime I see a natural log like this, I'm going to rewrite it as log base e to the x minus 4 squared. Here we have an e and we have an e, and they cancel. So my answer is just x minus 4 squared. Here I have a 2 to the log base 2 of 5x. So if I rewrite this, here I have a 2. My b is 2. My base is 2. What happens? They cancel. So my final answer is just 5x. So it's not tricky. It's not hard. It's just like knowing these two properties that we call them. If we know those, then it's okay. Log base 7 of negative 3. Here we have a negative 3. Remember that we cannot have a negative logarithm. So we would say that this answer is undefined. So just kind of a rule of thumb, a log of a negative number is always undefined. So we would write undefined like this. So the last thing we're going to talk about in this lesson, and then we are done, is graphing logarithms. They will always be done in the calculator, so we can't do these without a calculator, but they are inverses of exponential equations. So in 7.3, we graphed exponential equations with an e, and the things that we talked about were that the domain was always negative infinity to positive infinity, and then the range, oh my gosh, that keeps happening. Okay, we're good. And the range was our asymptote, which we called k, to positive infinity. Well, whenever you have an inverse, if you can recall from last semester, when you have an inverse, you switch x and y, right? You switch x and y. And so that's also going to switch my domain and range. So for my domain and range of a log, my domain is now going to be my horizontal or my vertical asymptote to positive infinity. And now my range is going to be negative infinity to positive infinity. So I want you to graph this in your calculator. So pause the video right now, and I want you to put in calculator. And I'm going to show you on the calculator what that's going to look like. So I have typed that in the calculator. This is log base 4 of x. You'll notice that the domain is from about 0 to positive infinity. So we would call this line right here a vertical asymptote. So my vertical asymptote would be at y equals, or this would be x equals 0, would be my vertical asymptote. And so imagine just like a vertical line that is dashed. It doesn't touch it, but it approaches it, and then it goes out to positive infinity. So domain would be from 0 to positive infinity, and then range would be from, it goes on forever, so negative infinity to positive infinity. Then if I wanted to plot some points, so if I wanted to see where does my x-axis, where is my x-intercept, where does it do at x equals 1, 2, 3, 4, I could go to menu, trace, graph trace. And I could type in, let's see, x equals 1. It's at 1, 0, 2, at 0.5, 3, 0.792. I could also do 4 at 4, 1. So what I would do is just type in numbers and put them out to the side. So I'm going to go back to my graph. So I'm going to make a little chart out to the right where I have x, y. You have 1, 0, 2.5, and 4, 1. So I'm going to graph those. And remember that you have an asymptote at x equals 0. It's different than the e equations because those were exponentials with a horizontal asymptote, but this is a vertical line. So I'm going to put in parentheses vertical because it is a vertical asymptote. Domain would be from 0 to positive infinity. Range is negative infinity to positive infinity. That's weird. That should not be there. There we go. And then I'm going to connect the dots. So it comes up like this. Connect the dots. You can just match it to your graph. For number 19, my domain, there's no k value. So I'm going to say that it's 0 to positive infinity. Range is negative infinity, positive infinity. So my asymptote would be at x equals 0. You can plug this in your calculator. So I want you to stop and do that right now. And I want you to find x values at 1, 2, and 3. I hope you have done that. I went ahead and did that, and I got 1, 0, 2, negative 1, 3, negative 1.59. So I'm just going to plot those. And then I'm going to connect my dots like this. So you'll notice that it's going down, like a decay kind of, and that is because of the number that is in front. So the 4 is bigger than 1, and this is from 0 to 1. So if it's a fraction, it's going to be going down like a decay. But you'll always have your calculator, so we don't really harp too much on having to know that. Okay, so for number 20 and 21, these are different. You'll notice that now they have stuff that is in parentheses. And so my my vertical asymptote will not be at 0 anymore. So what the number that I'm looking for, or what my vertical asymptote, it will always be the opposite of the sign that is in parentheses. So we have x minus 1. That means that my vertical asymptote is going to be at x equals 1. So it is not this value. You think that it would be 3. That's going to be the most common mistake that I see people make, but if you put it in your calculator, you will see. And the reason why is because it's a vertical asymptote. So we look at the number that's in parentheses, and then you flip the sign. So flip the sign of whatever you see in parentheses. So I'm going to put a little dashed line at 1. And so my domain is from 1 to positive infinity. Range is negative infinity to positive infinity. And if you put this in your calculator, I'm going to try it at x equals 2, 3, and 5. Again, it doesn't really matter what you put in your calculator. I just chose 3 points. So we have a point at 2, 3. Oops, did not mean to put that there. 2, 3. We have one at 3, 3.5. And we have one at 5, 4. So I'm going to connect the dots. Again, you'll always have your calculator. You will always have your calculator. So you should be able to tell what the vertical asymptote is. It's in the parentheses. So in parentheses, flip sign. So if it were just log base 4 of x and then close parentheses and then plus 3, then the vertical asymptote would still be at 0. The plus 3 does not matter. That's kind of like the shift up and down. So we'll talk more about transformations later, but you'll notice how this is at 2, 3. It's like it shifted up 3 points. Ideally, it would be right here on the x-axis. Okay, so the last one, it's x plus 5. So look in parentheses, I flip the sign. So my vertical asymptote would be at x equals negative 5. So I'm going to draw a straight line at negative 5. Domain, negative 5 to positive infinity. Range, negative infinity, positive infinity. Plot some points. So I'm going to choose negative 4, negative 3, negative 2. I end up getting negative 4, negative 5, and negative 5.59. So I'm going to plot those. 5 and negative 2, negative 5.59. And I'm going to match what I see in the calculator. So hopefully you put this in your calculator for practice. And it looks something like this. So that is the end of 7.4.